Hello everyone, this is Professor Keen. Today we'll be moving on to the next chapter, where we'll be looking at falling bodies and pendular motion. The reference for this chapter in A Student's Guide to the Great Physics texts is A Student's Guide, Volume 2 of course, Chapter 4. And this is from, once again, this is from Galileo's dialogues concerning two new sciences. So this is from Galileo's dialogues. This chapter begins with Simplicio. Remember, there's Simplicio, Sagredo, and Salviati having discussions about various scientific topics. This section begins with Simplicio expressing approval for Salviati's earlier demonstration that air, in fact, has gravity and not levity. So let me make a few comments about this. This is not something dealt with directly in this chapter, but it's something that they had talked about in a section from an earlier dialogue. And the idea of gravity and levity is an interesting topic. You'll notice that Galileo very often uses the term gravity when he refers to things falling. But it's good to keep in mind that Newton had not yet come around, and Newton had not yet made his universal law of gravitation. So although Galileo is using the term gravity, he means something very different than modern scientists mean by the term gravity. He's really inheriting this view of gravity that is more similar to the ancient Aristotelian view, and that is that objects have gravity in the sense that they have sort of an internal power that tends to make them fall downward. The gravity inheres or exists inside of an object as its tendency to move downwards toward the earth. That is the gravitas or gravity that an object has. You know, the modern view, the Newtonian view, I suppose you would say, is that the earth exerts a force on this rock, for example, when you drop it, and that force accelerates it downward. That is not the way Galileo is thinking about it. He is thinking about gravity as a property of rocks that tend to make them move downward. This is as opposed to levity. And the Aristotelian, the ancient view, is that air has levity. It tends to go up. So for instance, if you heat up, if you have a hot flame, that flame tends to rise upward because it has levity, whereas rocks and other objects like water tend to move downward because they have gravity. So that's sort of the reference frame within which Galileo is working. But he's calling into question the idea that air has levity as opposed to gravity. In fact, he talked about an experiment a bit earlier that demonstrated that air itself has gravity or a tendency to fall downward. How does he know this? Well, he talked about an experiment with a balloon. So if you take a rubber balloon or like a bladder of some sort, and you weigh it on a scale and measure the weight of this balloon when it's deflated, you'll find that it has a certain weight. And then if you take the exact same balloon and you highly inflate it, so there's compressed air inside of it, and tie it off, and once again place it on the scale, you'll find that the weight is slightly more. That is, an inflated balloon weighs more than an uninflated balloon. By a very small amount, maybe the weight of a few sand grains, but it was certainly measurable. And from that, Galileo concluded that air does not have levity as Aristotle had thought, rather it has gravity or gravitas, a tendency to fall downward. Anyhow, the three guys agree that these are excellent experiments that Galileo had carried out, and they then begin at the very beginning of the section to kind of praise Galileo for his ideas. Rather, they're praising Salviati. And in fact, there's an interesting quote here where Sagredo says, and I'll read from the text, "Not only this, but also many other of your views," he's talking to Salviati, who remember is representing the opinions of Galileo. Sagredo said, "Not only this, but also many other of your views are so far removed from the commonly accepted opinions and doctrines that if you were to publish them, you would stir up a large number of antagonists. For human nature," says Sagredo, "is such that men do not look with favor upon discoveries, either of truth or fallacy, in their own field of study when made by others than themselves. They call him an innovator of doctrine, an unpleasant title by which they hope to cut those knots which they themselves cannot untie, and by subterranean mines they seek to destroy structures which patient artisans have built with customary tools. So this is Sagredo, who's kind of talking about human nature. And there's a kind of a psychological analysis of how people, when they don't come up with an idea themselves, they tend to disparage the idea. And no doubt this is something that Galileo himself was experiencing with some of his ideas. They were being criticized in what he thought was an unfair way. Of course, those who were criticizing him did not think that they were being unfair at all. Okay, so with that introduction, let's go on to the topic of this chapter. And here, let me begin by asking this question, and this is something that the guys are going to be discussing. So how can we explore in some experimental way? How can we explore the retarding effects, that is the slowing down or the retarding effects that a medium has or exerts on a falling body? So you might recall in our last chapter, Galileo had focused on the effect of buoyancy. So when you drop an object in some fluid, the object tends to fall more slowly due to this buoyant effect. Okay, so how can we explore the retarding effects more generally that a medium has on a falling body? Is there some experimental way we can continue to explore this and think more carefully about this? And the answer that Salviati gives is that we can do this experimentally. We can simply drop objects and measure how much time it takes to hit the ground. So we can drop objects and measure the time of fall. And we can do this for various objects in different media. And the problem with this is that when objects fall, they fall quite quickly, and it's difficult to do careful measurements of the time of fall. So if you're going to drop a rock from the height of your head, it's going to fall and hit the ground very quickly. How do you measure this, especially when you don't have very high resolution timepieces? So a lot of times Galileo was measuring time in terms of pulses or heartbeats. So you'd put your fingers over your jugular vein and count how many pulses there are during the time of which something does something. Like when you drop an object, how many pulses would happen by the time it hits the ground? Of course, that's a very low resolution measurement. There's not going to be many pulses. You're not going to get a high precision. So this is not high precision. Is there a better way than dropping objects? Well, you could drop an object down a ramp. It's still falling, so to speak, right? So when you slide an object down a ramp, this first one, you're just dropping it straight down. Here, maybe you can put an object on a ramp and time how long it takes to go all the way down the ramp. And, one could make an argument that this isn't this exact same thing as just a falling object. After all, it's an object sliding down a ramp. So do they have to be the same? Not necessarily. But there's another problem with this, is that there's an interaction between this ball and the ramp. So the ramp is going to exert some frictional force, and it's going to affect the rate of fall. So you're not truly studying the falling of this object through the medium of air or water. You're studying the falling of this object through air or water plus the effect of this ramp. So that's a problem with this technique, is that the drag due to the ramp itself acting on the ball or whatever you're dropping. Okay, so this is maybe idea 1, idea 2, and there's a third idea that Galileo comes up with. And this is, instead of dropping objects, remember the idea here is if you drop an object, it's hard to measure it with high precision, but if you drop something from a very high height, then any differences in the time of fall of two objects is going to be amplified by the amount of time it's falling. The problem is it's hard to find a cliff that's high enough to be able to measure these things readily. So what Galileo says is he says, well, instead we can repeatedly drop something over and over again. The best way to do that is using a pendulum. What is a pendulum? Well, you take a ceiling and you take a string and you take a ball and you release it and it swings downward, so it's falling, but then it swings back up and then it swings back down again and it repeats itself, right? So this object is swinging back and forth. And if you took two different pendula, maybe one that's got a lead ball and another one that is made of maybe cork, different materials, if there's a small difference between the time of fall of this one and the time of fall of that one, it would be hard to measure if it was just one swing. But hopefully over the course of many, many swings of these things, any small differences would be amplified. So this is going to presumably allow you to measure the effect of the medium on a falling body in a more precise way than either method 1 or method 2. So this is the preferred method. This is what Galileo is going to be studying. He's studying the relationship between falling bodies and pendular motion. That's why this chapter is titled that. Okay, so what happens? Let's suppose that you take, this is the experiment that Galileo imagines, you take two pendula, you make both of these strings exactly 4 cubits long. Okay, so that has a length of 4. I know it doesn't look like it here. This one looks shorter than that one, but that's just because of a drawing error here. And let's suppose you make one of them of cork. So I'm going to color one of them brown. That's cork. And the other one, you make it of lead. And I'm going to make this one, I don't know. I'll make it kind of this greenish blue color. This one is lead. Okay, so they're different weight objects, but they're being suspended from strings that are exactly the same length. And if you were to let these swing back and forth, what happens? Well, Galileo tells us what happens. He said if you measure the time period, that is the time it takes for the cork to swing back and forth once, I'll call that T sub C, and the time it takes for the lead to swing back and forth once, I'll call that time of lead. If you measure that time, you find that the two times are equal. And not just for one swing. After all, it's hard to see any small differences for one swing, but he says they have equal periods, so different weight objects swing with the same period T for 100 swings, 1,000 swings, he says. So even if you let these things swing back and forth 1,000 times, they will stay perfectly synchronized with one another. The same period. They stay synchronized because it takes the same amount of time to swing back and forth. And this is perhaps strange. One might think that they would have different times depending on the weight of the object, but Galileo is saying the opposite. He's saying no, they have the exact same time of swing regardless of the weight of the object. This, of course, is provided they have the same length of string. We'll come back to the case where they have different lengths in a little while. But this is irrelevant what the weight of the object is. So different weights, same period. The other thing that he noticed is that if you have different heights, so different initial angles. So you might imagine, for example, initial angle, I'll call that angle theta. Maybe you swing this one back, you have two lead pendulums that have the exact same 4 cubit length string, and you pull one back, maybe the angle of one of them, you pull it back to an angle of 6 degrees. And you do another pendulum with an angle of, let's say, 12 degrees, and another one with an angle of 20 degrees. Different initial angles, and he found still that they have the same period. So it doesn't matter what angle you pull them back to, they will swing back and forth with the same period. So different angles, same period, different weights, same period. That's very interesting. Now, I should say something right away that this second point that Galileo is making, if you do this with very high precision, you will find that the period does depend very slightly on the angle through which you swing it, but that requires more careful analysis than what Galileo was capable of doing at the time, or at least than he did at the time. He claimed that they had the exact same period. If you do this carefully in the laboratory, you will find that the different angles do have different periods of swinging back and forth. So this is a case where Galileo wasn't quite correct. There's an issue that is brought up also, this is right around page 48, that these two objects, let me go back to this case right here with the different angles. If different angles have the exact same period of time, so if different angles and hence different arc lengths, have the same period, then the speed must be different passing through the bottom. When passing through the bottom of the swing. This is something that Salviati points out. After all, if you take one of them, you pull it back to 6 degrees and let it go, it'll swing back and forth. It's going to have a fairly short arc length. Let me draw this out. So if you have a 6-degree angle, it's going to swing back and forth with this arc length right here. That's going to be some distance arc length, we'll call that S1. Whereas another one, if you have a bigger angle and it swings back and forth, it's going to have a larger arc length S2. So this would be the arc length that the one swings back and forth when you start it from a 20-degree angle. This is going to be the arc length that swings back and forth through when it starts with a 6-degree angle. If they travel different distances in the same amount of time, then they must be going at different speeds during their swing, since the speed that an object is moving is equal to the distance it travels during a particular time interval. And a larger distance for the same time means a larger speed. So this is something that Salviati points out. Although they have different periods, they do actually have different speeds when swinging through the bottom. Okay, so let me pause there and I'll pick up this discussion next time.